Take a little blob of mercury, just the silvery liquid you might have seen in an old thermometer. Cool it down. Cool it past the point where it freezes solid. Cool it past where any ordinary chemistry happens. Cool it down to within a few degrees of absolute zero, which is the coldest temperature that can possibly exist anywhere in the universe. And then send a current through it. Something extraordinary happens. The resistance vanishes, not gets small, not approaches zero in some sneaky asymptotic way. It goes to zero. Exactly, perfectly, mathematically zero. You can start a current circulating in a loop of this stuff and walk away. Come back a year later. The current is still there, exactly the same. Come back 10 years later. Still there. There is no decay. There is no heating. The energy is not being eaten by friction the way it always is in every other piece of wire that has ever existed. Now I want you to sit with that for a moment, because in normal physics this should be impossible. Electricity always loses energy when it flows. Always. That is why a flashlight battery dies. That is why power lines hum. Resistance is the universe taking its cut, and as far as I have ever been able to tell, the universe never works for free. Except, apparently sometimes it does. This is one of the strangest things in all of physics, and the story of how we figured out what is going on inside that little blob of mercury, and why we still cannot quite finish the job, and why we cannot yet make a piece of wire that does this trick at room temperature, is what I want to tell you about. So let us play detective. The first clue, the one that started everything, was an accident. It usually is. Around the year 1908, there was a Dutch physicist named Heike Kamerlingh Onnes, and he was obsessed with cold. Not snowy cold, not winter cold, real cold. The kind of cold where ordinary matter starts to behave like it is made of something else entirely. He was in a race with several other laboratories around Europe to liquefy helium, which was the last gas that nobody had managed to turn into a liquid. To liquefy helium, you have to get down to about 4 degrees above absolute zero. That is colder than the dark side of Pluto. That is colder than anything in the natural world. And Onnes won the race. He squeezed and cooled and squeezed and cooled, and one day in his laboratory in Leiden, helium became a liquid in a glass jar. He had built the coldest place in the universe inside a basement. Now what do you do with the coldest place in the universe? You start dunking things in it. That is what he did. He dunked metals in it to see what happened to their electrical resistance. You have to remember what people thought back then. They thought resistance came from electrons bouncing around inside a metal, knocking into atoms that were jiggling because of heat. The hotter the metal, the more the atoms jiggle, and the more the electrons get knocked around, and the more resistance you get. So the colder you go, the less the atoms should jiggle, and the lower the resistance should fall. The question was, what does it do at the very bottom? Some people thought the resistance should drop smoothly to zero. Some people thought the electrons themselves would freeze in place, and the resistance would shoot up to infinity. Nobody was sure, so Onnes decided to check. He picked mercury, because he could distill mercury to extreme purity, and a pure metal would give him a clean answer. He took a thin column of mercury, cooled it down, and watched the resistance. The resistance dropped, just like everybody expected, slowly, smoothly. Then, at 4.2 degrees above absolute zero, the needle on his measuring instrument did not just dip. It crashed. It went straight to the bottom of the scale and stayed there. His first reaction, of course, was that the equipment was broken. That is always your first reaction when nature shows you something it should not. He checked his instruments. He checked his wires. He checked his cold bath. He repeated the experiment. Same result. The resistance of mercury, below this magic temperature, was not just small. It was, as far as he could tell, absolutely zero. He gave it a name. He called it superconductivity. And then he and everybody else in physics had to figure out what on earth was going on. So let us play detective. What do we actually know from this first clue? We know that something happens at a specific temperature, like ice melting, but in reverse. Above this temperature, mercury is a normal metal. Below it, mercury is something new. There is a sharp boundary, a phase transition, just as sharp as the boundary between water and ice. That is suspicious. That tells us this is not just electrons being lazy. This is matter doing something it has not done before. We also know the resistance is genuinely zero, not just very small. How do we know? Because Onnes and the people who came after him put currents into rings of superconductor and watched them. If the resistance were even a tiny bit non-zero, the current would die down over time, the way a swing dies down because of friction. But these currents, in some experiments, ran for years without any measurable decay. Years, with no battery, with no power source, just spinning in a closed loop, like a planet that has forgotten how to fall. Now, the first guess anybody makes is the obvious one. Maybe a superconductor is just an extremely good conductor. Maybe the electrons have, for some reason, stopped bumping into things. The lattice has gone quiet. The impurities have gone to sleep, and so the resistance drops to zero by accident, the way a sled on perfect ice would slide forever. This is a sensible guess. It is also wrong. And the experiment that proved it was wrong is so beautiful that I want to walk you through it carefully, because it is the moment in this story where we go from a small mystery to a big one. In the early 1930s, two German physicists named Walther Meissner and Robert Ochsenfeld did something straightforward. They took a piece of metal that becomes a superconductor when you cool it, and they put it in a magnetic field. Then they cooled it down past the magic temperature. What should happen if a superconductor is just a perfect conductor? Well, here is the rule for perfect conductors. A perfect conductor traps any magnetic field that was already passing through it. The currents in the metal will lock that field in place and refuse to let it change. So if you turn on a magnetic field first, then cool the metal, the field stays inside. If you cool the metal first, then turn on the field is kept out. The metal remembers what was happening when it became perfect. What did Meissner and Ochsenfeld actually see? Something different. They saw that no matter what you did first, no matter what the history was, when the metal became a superconductor, the magnetic field was pushed out of it, squeezed out, expelled, as if the superconductor were physically allergic to the magnetic field. This is called the Meissner effect, and it is the moment when the easy explanation died. A perfect conductor would let history matter. A superconductor does not. A superconductor always reaches the same final state, no matter how you got there. That means it is not simply a metal where the resistance has dropped to zero. It is something more. It is a new state of matter. It is to a normal metal what ice is to water. A different phase, a different way of being. You can do something wonderful with this. You can take a tiny magnet and lay it on a chunk of superconductor, and the magnet will float. It hovers in the air, completely still. Not balanced, not spinning, just sitting there, suspended, as if the rules of the world had been quietly rewritten in that one little corner of your laboratory. People have been doing this trick for decades, and it never gets less astonishing. So now we have two clues. Resistance is exactly zero, and magnetic fields are completely expelled. Whatever is happening inside the superconductor is happening to all the electrons at once, in a coordinated way. They are not just flowing freely. They are doing something together. This is where the mystery gets strange. Because if there is one thing electrons do not like to do, it is cooperate. Two electrons, sitting next to each other, repel. They both have negative charge. Like charges push apart. Always. Everywhere. That is one of the most basic facts of electricity. The kind of thing you learn before you learn anything else. So how can a vast collection of electrons all suddenly decide to march in lockstep when their natural instinct is to fly apart? For decades, nobody could answer this question. The greatest minds in physics looked at the problem and walked away. Einstein took a swing at it and missed. Heisenberg took a swing and missed. Bohr, Pauli, Feynman, all the heavyweights, everybody. The problem just sat there, mocking them. Mercury kept on being a superconductor. Lead kept on being a superconductor. Tin, niobium, aluminum, dozens of metals all kept doing the impossible thing, and nobody could explain how. Almost half a century went by. Half a century. From the discovery of the effect to the discovery of why. That is unusual in physics. Usually we are faster than that. But this one was hard. So let us follow the trail of clues, the way the people who eventually solved it did. The first clue came from looking at different isotopes. An isotope is just a version of an element with a different number of neutrons in the nucleus, which means a heavier or lighter atom but identical chemistry. If you take mercury made of one isotope and measure its critical temperature, the temperature where it becomes superconducting, you get a number. If you take mercury made of a heavier isotope, you get a slightly lower number. The heavier the atomic nucleus, the lower the temperature where superconductivity kicks in. Now think about that. If superconductivity were purely about electrons doing electron things, it should not care at all how heavy the nucleus is. The nucleus is just a chunk of dead weight sitting there, holding the atom in place. Its mass should not matter to what the electrons do. But it does matter. So whatever superconductivity is, it has something to do with the nuclei. The nuclei are part of the story. What can a nucleus do that involves its mass? It can vibrate. The atoms in a metal are not glued to fixed spots. They sit in a lattice, like a crystal, and they jiggle around their equilibrium positions. These jiggles travel through the metal as waves, the same way sound waves travel through air. We call these vibrations phonons. They are the sound of the material at the atomic level, and how fast a nucleus vibrates depends on how heavy it is. A heavier nucleus jiggles slower. A lighter nucleus jiggles faster. So the isotope clue tells us that the lattice vibrations matter. The phonons are part of the story. This was a huge clue, because it suggested, for the first time, that maybe the electrons in a superconductor are doing something through the lattice. Maybe they are not interacting with each other directly. Maybe they are interacting with each other indirectly, by way of the atoms in between. Picture it like this. Imagine you and I are standing on a big trampoline, far apart. You weigh, let us say, the same as I do. Now I take a step. The trampoline dips under my foot. Because the surface is stretched, the dip propagates outward, and a little wave of the trampoline going down passes under your feet. You sink slightly. Now, from your point of view, you got pulled toward me. Even though I am not touching you, even though there is nothing between us, the trampoline carried an attraction from my position to yours. Two electrons in a metal can do something similar. The first electron passes through the lattice and pulls the positively charged nuclei toward it slightly, because opposite charges attract. The lattice deforms a tiny bit. That little patch of extra positive charge, that little dent in the lattice, sits there for a moment, because the heavy nuclei are slow to move back. Then a second electron comes along and feels that little patch of positive charge and gets attracted to it. So in effect, the second electron is attracted to where the first electron was. This is a strange kind of attraction, and it is weak, and it is only effective at very low temperatures, because at higher temperatures the lattice is jiggling so much from heat that you cannot pick out the tiny dent that one electron makes. But it is real, and it is, just barely, strong enough to overcome the direct repulsion between two electrons, if conditions are right. This was the breakthrough. The man who first wrote down the idea clearly was Leon Cooper, an American physicist working with John Bardeen and Robert Schrieffer in the late 1950s. He showed mathematically that two electrons in a metal at low enough temperature can form a bound pair. Not a chemical bond, not anything you would see under a microscope. A delicate, long-range, almost ghostly pairing where the two electrons stay correlated even though they are far apart and never touch each other. The pairs are huge. A single Cooper pair, as it is called, can be hundreds of atoms across, with countless other electrons swimming around inside it. They overlap with each other constantly. They are not like two people holding hands. They are like two dancers in a packed ballroom who are tracking each other across the room without ever making contact. Now here comes the prettiest part of the whole story. When two electrons pair up like this, the pair behaves as a unit very differently from a single electron. A single electron is what we call a fermion, which is a particle that hates to share its quantum state with other particles like it. Fermions are antisocial. That is why electrons fill up shells in atoms, one to a slot. They cannot be on top of each other. But a pair of electrons, two fermions stuck together, behaves like a different kind of particle entirely. It behaves like a boson, and bosons are the opposite of fermions. Bosons love to share. They love to pile up in the same state. Given the chance, they will all condense into the lowest energy state available, all at once, and form a single coherent entity. So in a superconductor, when you cool it below the critical temperature, the electrons pair up into Cooper pairs, and then those pairs all condense into the same quantum state. Every pair, throughout the entire piece of metal, behaves like part of one giant collective wave. The whole superconductor becomes, in a sense, a single quantum mechanical object. A whole hand of cards, flipping in unison. And once you have that, the strange properties make sense. Why does current flow without resistance? Because to slow one electron down, you would have to scatter it, which would mean breaking it out of the collective. But it is bound to all the others. You cannot disturb just one. You would have to disturb the whole collection at once, and that takes a very particular amount of energy, called the gap. If the temperature is below a certain level, there simply is not enough thermal energy floating around to break a pair. So the electrons cannot scatter, so they cannot lose energy, so the current flows forever. Why does the magnetic field get pushed out? Because the collective wave that all the pairs are sharing extends through the whole superconductor, and when you try to push a magnetic field through it, the wave shifts in just such a way as to set up currents that exactly cancel the field inside. The expulsion is automatic. It is built into the geometry of the collective state. 3 men, Bardeen, Cooper, and Schrieffer, wrote all this down in a complete theory. We call it BC's theory, after their initials. They published it around 1957, and it was such a beautiful piece of work that it instantly explained everything that had been puzzling about superconductors for 46 years. The temperatures, the gap, the isotope effect, the Meissner effect, the persistent currents, all of it fell out of one set of equations. You should pause here, because in physics that almost never happens. Usually a theory explains some things and leaves loose ends. BC's tied the whole package up. Bardeen, by the way, won 2 Nobel Prizes in his life. The first was for inventing the transistor, which is, a small thing. The second was for figuring out superconductors. Most physicists would consider one of those achievements enough for an entire career. So now you might think the story is over. We have a beautiful theory. We understand what is going on. End of mystery. Except no. Because this is where the trail goes cold, and a new mystery picks up. The BC's theory makes a clear prediction. It tells you what kinds of materials can be superconductors, and at what temperatures. The pairing happens through phonons, and phonons can only carry so much binding energy, and so the critical temperature, the temperature where superconductivity sets in, has a ceiling. By the most generous estimates anybody could come up with, this ceiling is somewhere around 30 degrees above absolute zero. Maybe 40 in extreme cases. No higher. The theory simply cannot push the binding strong enough to allow Cooper pairs to survive at warmer temperatures. It is mathematically not possible within the framework. For decades, this was the situation. Physicists looked for new superconductors. They found dozens. All of them obeyed the rule. All of them had critical temperatures below 30 Kelvin, well in line with what BC's predicted. The theory looked safe. The ceiling looked real. And then, in 1986, 2 researchers in a laboratory in Switzerland named Bednorz and Muller found a material that broke the rule. They were not even working with a normal metal. They were working with a strange compound called a copper oxide, a kind of ceramic. Ceramics are usually not conductors at all. Ceramics are what you make insulators out of. The cup you drink your coffee from is more or less a ceramic. The idea of a superconducting ceramic was, frankly, ridiculous. But these two men were patient and stubborn, and they tried it. Their first material was a superconductor at 30 Kelvin, right at the ceiling. Already strange, but maybe a fluke. Then within a year, other groups had tweaked the recipe and pushed it to 70 Kelvin. Then 90. Then 130. The ceiling shattered. By the time the dust settled, there were ceramics that became superconductors at temperatures more than 4 times higher than anything BC's theory said was possible. And nobody knew why. To this day, nobody fully knows why. I want you to feel how strange that is. We have, in our laboratories, materials that do something we do not understand. We can cool them down. We can watch them lose all resistance. We can float magnets above them. We can wire them into circuits. We can write papers about them. But if you ask me, or anybody else, what holds the electrons together in those materials, I have to tell you honestly that we are not sure. We have ideas. We have many ideas. We have far too many ideas, which is usually a sign in physics that nobody has the right one. But we do not have a clean theory the way BCs gave us a clean theory. We know the electrons in these materials are pairing. The Meissner effect is there. The gap is there. Everything you would expect from paired electrons is there. So that part of the BC's picture survives. But the pairing cannot be from phonons. Or at least, it cannot be only from phonons. The numbers are wrong. The temperatures are too high. Some other glue must be holding the pairs together, and we do not know what kind of glue it is. There are guesses. The most popular guess is that the pairing comes from magnetic interactions, from the way electron spins push and pull on each other in a layered crystal. There are other guesses too. Some involve lattice fluctuations of an unusual kind. Some involve electrons forming patterns of stripes or checkerboards before they pair. Theorists have written tens of thousands of papers about this problem, and the field has not converged on an answer. So we have a working physics, a phenomenology, that lets us use these materials, and we have a mystery underneath it that nobody has cracked. Now we get to the question you really wanted to ask. Why can we not make a superconductor that works at room temperature? Why does this trick require us to drag a tank of liquid helium, or at best liquid nitrogen, into the room every time we want to use it? The answer comes in 2 layers. There is the BC's layer, the answer for the metals we understand, and there is the layer for the ceramics that we do not. For the BC's materials, the answer is mathematical. The binding energy of a Cooper pair, the energy that holds the 2 electrons together against their natural repulsion, depends on how strongly the electrons couple to the lattice vibrations, and on the typical frequency of those vibrations. Lattice vibrations cannot vibrate arbitrarily fast. They have a maximum frequency set by how stiff the bonds are between atoms and how heavy those atoms are. So the binding energy has a ceiling, and the temperature where superconductivity disappears is roughly proportional to the binding energy. A pair binds with some strength. Heat carries enough energy to disrupt that bond above a certain temperature. End of story. To get higher temperatures, you would need stronger glue, and phonons cannot provide it. For the ceramic high-temperature superconductors, the answer is a shrug and a question mark. We do not know what is gluing the pairs together, and so we do not know how strong it could in principle become. We do not know whether there is some yet undiscovered material in this family that would superconduct at room temperature, or whether we have already pushed the trick about as far as it will go. We are genuinely, openly, in the dark. There is one direction people have explored, which is to take very ordinary substances, like simple hydrogen-rich compounds, and squeeze them under tremendous pressure, the kind of pressure you would find inside a planet. Under enough pressure, the lattice becomes so stiff that phonons can carry much more binding energy, and the BC's critical temperature can climb. People have made materials in diamond anvils, with pressures comparable to the pressures deep inside Jupiter, that may superconduct at temperatures astonishingly close to room temperature. But you cannot run a city on a piece of wire that requires the pressure of a planetary core to keep it working. It is a beautiful piece of physics. It is not a practical material. So we sit at this strange historical moment where we can do half of an impossible thing. We have superconductors. We have wires that carry current with no loss. We use them in medical scanners, in particle accelerators, in research labs. They work. They are not science fiction. But they all need to be cold. Some of them need to be a little cold. And some of them need to be incredibly cold. And the ones that need to be incredibly cold are the ones whose physics we understand. And the ones that need to be only a little cold are the ones whose physics we do not understand. Cold costs energy. Cold costs equipment. Cold means you cannot just string a superconducting wire down the street. Imagine, for a moment, that we crack the problem. Imagine that somebody, someday, finds the right material or the right principle or the right structure that would let electrons pair up at room temperature without any cooling at all. What would change? I will tell you, every wire in the world becomes lossless. Every power line, every transformer, every motor, every magnet. The electrical grid stops dissipating something like 10% of all the power it carries as heat in the wires. Magnets become absurdly strong because you can run any current through a coil and it just sits there forever, building up enormous fields without overheating. Trains float instead of rolling. Hospitals scan you with machines the size of a microwave oven instead of the size of a room. Energy storage becomes trivial because you can park a current in a loop and come back to it next month, fully charged. Whole industries that depend on cold, expensive, fragile cryogenic systems suddenly become as easy as plugging in a lamp. The reason this matters, and the reason this problem keeps physicists up at night, is that we know it is allowed. The universe has done it before. The universe has chosen, in mercury at 4 degrees, in lead at 7 degrees, in copper oxide ceramics at 130 degrees, to let electrons pair up and behave like a single thing. It has demonstrated the principle. It has handed us examples. The puzzle is finishing the climb. The puzzle is finding the version where it works in the open air on a kitchen table without a tank of liquid anything. Maybe it is impossible. Maybe there is some hidden law of nature, something we have not noticed yet, that says no. Maybe the binding energy cannot climb that high in any material, ever, anywhere, for reasons we do not yet have words for. Or maybe it is sitting there waiting, in some ordinary-looking compound nobody has thought to test, and a graduate student somewhere is going to drop a sample of it into an apparatus and watch the resistance hit zero at a temperature where you could hold the sample comfortably in your hand. I genuinely do not know. Nobody does. That is the honest answer, and you should be a little suspicious of anyone who tells you they know for certain in either direction. What I find marvelous, though, when I sit with this whole story, is the shape of it. We started with a man dunking a piece of mercury in a tank of liquid helium and being puzzled by what he saw. That puzzle propagated through 46 years of theoretical physics, drew in some of the greatest minds we have ever produced, and finally yielded to a beautiful piece of mathematics involving paired electrons floating through a lattice like dancers in a crowded room. And then the puzzle came back. A new generation of materials laughed at our beautiful theory and proceeded to do the impossible at temperatures we said were forbidden. And now we are back to the beginning. We have the phenomenon. We do not have the explanation. We are guessing. We are arguing. We are running experiments and writing papers and disagreeing with each other. And somewhere in all this confusion, the answer is hiding. Because the answer always is. Nature is not coy in the long run. She tells us what she is doing, eventually, if we ask the right question. We just have not quite figured out the right question yet. When you next see a magnet floating above a chunk of dark gray ceramic in a video, or when you next walk past one of those big medical scanners in a hospital, I want you to remember that there is a quiet revolution going on inside that machine. Electrons are doing something they were not supposed to be able to do. They are paired up across vast distances. They are gliding without friction. They are behaving like one unified thing, every last one of them, in lockstep, in coherence, in something that almost looks like the cooperation of crowds. And we, the great clever apes who built the machine, are still standing in front of it, scratching our heads, asking the simplest question of all. How? Tell me if you had to bet. Which would you put your money on? Will somebody crack room temperature superconductivity in our lifetime? Or is there a hidden rule of nature quietly forbidding it forever?